So hopefully you're seeing Adventures in Concrete right now. All right. So my plan is to take the first half hour, talk a little bit about my setting, because the kind of place that you teach from influences how you could do your teaching. To describe the project, talk a little bit about the chemistry of concrete and the chemistry side of this project, which was actually a dual chemistry physics project, and then leave the second half of the hour for whatever people want to delve more into. If it's the way I do my so-called challenge labs, if it's the way I assess soft skills or content, if it's the details of the infrared camera that we used. So please feel free to ask questions at any time, but I may just make a note to myself and give you the short answer and say, we'll dig into that in the second half. I knew that I could talk for more than the time we had, so I figured I'll do the brief part, and then you can, as a group, direct where you want things to come from. So I teach at a public high school on the coast of Maine. It's got 750 students. My classes are a maximum of 20. They're usually like 18 to 20. We do have, and it doesn't affect the chemistry side of this project, but it does affect the physics side of this project, a new innovation or maker space, which means a shop with people that know how to help kids build things. My honors chem class that this particular project involved are a mixture of 10th and 11th graders who have all taken or are concurrently taking honors algebra 2. The physics side of things are 11th and 12th graders, and that's a CP level algebra-based course. My students are a mixture of socioeconomic classes. Sadly, Maine, where I teach, ranks 50th out of 50 in diversity. So we're not a very diverse population in that way, but we are diverse socioeconomically. Oh, and my classrooms all have a lab that's in the classroom. It's a one-room lab classroom space. You don't have to switch spaces depending upon what you're doing. So the overview of this project was that my chemistry classes designed and made small bars of mortar, and we'll talk about why they're mortar and not concrete. This was a part of it was an application of studying the heat of reactions. We had a really boring lab applying how the rate of a reaction was affected by the temperature of the reaction, and I wanted something that was more applicable. We happened to be 10 miles away from the only remaining cement manufacturing plant in New England, so it was kind of appropriate. They monitored the temperature of the bars as they cured, which is an important factor in concrete and is the connection to the content. And then they shipped the bars. They had to pack them up, and I transported them to my physics classes, and my physics classes tested the tensile strength of the bars as a part of their work on force diagrams and Newton's laws and so forth. And the physics classes then sent a report back to the chemistry classes on the tensile strength of the bars. They couldn't talk to the chem classes, they could only send a report. And they also sent the broken bars went back. The chemistry classes then took their temperature data, their composition data, the strength data, and tried to make some claims about how the curing temperature and the composition and the tensile strength were related. So this was a cross-disciplinary project that involved, I was the only one teaching this particular level of physics, but there were 2 of us teaching chemistry that shared it. So we had 4 chemistry classes and 2 physics classes participated in the project. So a little bit about concrete and cement. Cement is the glue or the binder that holds concrete blocks together. Concrete is one of the most ubiquitous building materials in the world. Making cement itself is a greenhouse gas problem, but once you have made the cement, making concrete and so forth is very low impact on the environment. And it's a very strong structural material. So it's relevant. Yeah, anybody that's ever like fixed their patio has probably played with concrete. So cement, usually by Portland cement, Portland, Maine, is the glue that holds things together. When you combine the Portland cement and sand and water, you get what's called mortar that you might see in between bricks in a brick wall. And if you add rocks, some kind of aggregate, stones, rocks, to the mortar, then you have concrete. So concrete is a mixture of all these things. The expert that I worked with, I had sat in on a class of civil engineering and gotten fascinated with concrete. And he suggested, because we were making very small bars, that we should do mortar and not concrete, because the size of the aggregate, the little stones we would use, would be so big compared to the bars that it would really affect the tensile strength. It would not be very precise to measure the tensile strength. There'd be too much variability. So we made mortar instead. So what we were playing with was mortar. I have included in the folder of stuff my entire slideshow that I gave my chemistry students on the chemistry of concrete and cement, but I want to share a couple things here because it influences the project. So to make cement in the first place, you take limestone and you heat it up in a big kiln. And by big, I mean it's like 400 feet long, which breaks it down into lime, calcium oxide. And that combines with silica that's in the clay that's also present in this stuff to make these calcium silicates. And these are the main ingredients that are going to create the structures that create the strength in mortar and concrete. When you add water to your cement dust, and your cement dust can sit around for years, when you add water to it, each compound in that cement dust, and there's a bunch of things in it, all react with the water to form crystals. And those crystals expand in the spaces between the cement grains and the sand grains and the air pockets, and they literally grow into those cement grains and sand, and they tie everything together. And that's what holds concrete together. And there's sort of a picture below of some of the different kinds of crystals that form. There are multiple processes going on. They're not all completely understood. It's rather, it can be quite complex. There are actually 5 stages to forming concrete, and the temperature at those stages tells you what's going on. And this was the big connection to heat of reaction. So the first thing that happens is that you mix it up, and it rapidly, there's actually heat that, they don't have the very first part of this. It heats up and cools down pretty quickly. And that's the formation of a material that does not actually strengthen the concrete. It's got the wonderful name of etrigite. And they're formed from the gypsum that's in the cement dust and water. It uses up a lot of the water, but the material is still plastic. So when you mix this stuff together, and then you see the people pouring this concrete, these crystals are already forming, but the stuff is still moldable, movable, and so forth. But in a few hours, after it goes through a stage of dormancy, then the thing heats up again. And that's because of 2 main reactions to form what are called these calcium silicate hydrated crystals. There are 2 major forms of those. And so it doesn't just go up and down, it goes up and then it bumps down because one reaction is quicker than the other. But these crystals form, they release heat. And as they form, these are the things that are growing into and gluing everything together. Once the concrete has set and you can go, build your barn on top of it or whatever, it hasn't actually finished reacting. Concrete will continue to react for years. In fact, some of the Roman concretes probably kept curing for centuries. The reactions slow way down because there isn't a whole lot of available reactants, but it keeps getting stronger. It's one of the interesting facts about concrete is that depending upon where you put it, like concrete that you put underwater is a little different, but concretes will continue to gain strength over time. So it's this temperature profile that we were interested in looking at as a guide to what was happening inside on the concrete, or rather mortar. So what did the chemistry students do? I'm going to show you some pictures and then go back to the details. This here in the center, you'll see a little mold. These are sold for making ice cubes for sports bottles with a narrow neck, so you can put the long ice cube down. So these made 4 bars of concrete. That's a 1,000 milliliter beaker in there for comparison, and an iPad, so you can kind of see the size. And then sitting on top of it is an iPad with this infrared camera. And the infrared camera, you may be able to see 4 faint white crosses on that red field. The camera, you can pick up the 4 spots on its field and it will record temperatures. And you can see down below a combined temperature graph of the four spots on one of the team's molds. Each team made 1 mold of 4 bars, so they had 4 replicates, and so forth. Let me back up, go through some steps. So the students have already gotten some information about exothermic, endothermic reactions, heat of reaction, and so forth. Then I give them some background on concrete basics, and they have a formative quiz. This is an online multiple choice quiz. I've actually put the questions as a file in the folder, and they can retake this multiple times. It's just sort of a reminder of these are the important points about the chemistry that you should be remembering as we go through this process. Then I give them the lab challenge, which is you want to design the strongest possible mortar, the proportions of sand and water and cement dust. You want to make the strongest possible bars that you can. And so they have, and I'll talk about the formation. So they design their proportion as a class. We have 5 cameras, so they can make 5, each class can make 5 different variations. And because of the molds, they get 4 replicates with each variation. So they make the mortar, and they set up the cameras and record the curing temperatures. And in 2 days, the bars have cured, and you send them to physics, and physics measures their breaking strength, sends back the data. The chemistry kids then get together, look at their temperature data, their strength data, and their compositions, and see what they can come up with for claims. And then in order to present this, and to keep 20 people all working, I have over time developed what we call product teams. So some people are speakers. They have to present this orally as if they were at a conference. Right? It's not, you're not writing up a lab report. You're presenting it as if you're going to a conference. So there's a speaker team. There's an audio-visual team that creates the PowerPoint or slides or whatever they want that the speakers need. There is an outreach team, which has to put together some kind of a display in the hall. This year, they were using a glass case. Sometimes they use bulletin boards that has to explain this project to anybody in the school that walks by. I usually use our French teacher for an example because they know that math and science is not his Monsieur Man's big forte. He's a boat captain when he's not Frenchifying. And I said, you know, like if Mr. Man can understand it. So that's a different way of explaining it. And then there's usually a study team that puts together a packet of study materials for everybody to use because they're going to get an individual assessment. They're going to take an individual sort of test on both the concrete and the details of the, like, what was the claim and how do you back it up, claim evidence reasoning, that kind of stuff. They turn in a lab notebook, which is really more field notes. It's like, did you record everything as you go? It's not a you know, complete lab write-up and so forth. And there's a bunch of reflections and things that go on. So that's kind of the arc of the project. It does take time, and you do have to have a pause in the middle because while things are being sent over to physics, you may not get them back before the next class, depending upon when your physics classes can get down to and measure the strength. So you may have to have other things going on in the classroom as you're working on that. Does that sort of arc make sense? Feel free to ask clarifying questions as we're going. All right. You can see in the upper right, I included a physics picture so you could see what the physics kids, if you've ever done balsa wood bridge testing, then you know the kind of thing the physics kids came up with to test the tensile strength. And then in the bottom is an example of one of the displays. We kind of combined it. The physics students had a display of their machines in the bottom parts of this big glass case, and then the chemistry students had displays above them of their side of the project, which worked out pretty well. What kinds of things do you need to do this project? Well, on the chemistry side, you need Portland cement dust. It doesn't come in small packages. I could not find, I ended up with a big bag of Portland cement, which not only will last this project for the next 20 years, but anybody in the department that has small projects probably can borrow it for that. You need sand. This year, we were just asking the question, what's the best proportion? Next year, we're going to take that information. The next classes will be given what's the best proportion, and they are going to play with different kinds of sand, finer sand, coarser sand, more rounded sand, sharper edge sand, whatever I can find. You need infrared cameras if you want to measure the curing temperatures, and we'll talk in more detail about those. And you need some kind of devices to collect data. Because you're going to be collecting data for more than a couple of minutes, you can't ask the students to use their iPad or their phone to collect the data. So we borrowed some from, we're a one-to-one iPad school, and the school gave us, lent us out 5 iPads that we could use for the course of the experiment, which, we then turned in. On the physical side, you need the molds. They're pretty cheap. Got them on Amazon. You need some kind of, we used little Tupperware containers to mix the mortar in. One of the things you don't want to do is use any of your nice lab glassware to make mortar. This is messy. In fact, the first thing we do in the chem lab is we cover all of the tables with the giant garbage bags that the maintenance has. And this way, any mortar is not going to stick to your lab counters. You're not going to have cement dust flying around. You can fold that up and toss it. May not be the greenest way to take care of it, but you do not want to use graduated cylinders and things from your lab. So I got some cheap plastic Tupperware that was big enough for each team to make a mold's worth of stuff. We played around with, I had some spoons, I had some rubber spatulas for mixing up the mortar and then transferring it. You could probably use popsicle sticks, would probably work pretty well. I bought some cheap measuring cups at the dollar store because I didn't want, you don't want to use your nice graduated cylinders for measuring out the materials. I bought a container. I think it was actually like a milk or juice thing that you'd put in the refrigerator, that we put a reasonable amount of cement dust in that had a top and had a lid. You could use any kind of container for that, because you don't want an 80-pound bag of cement dust open in your lab. That just, the more, even thinking about that gives me the shivers. And then our sand was in fairly small containers. It was left over from years ago from, I don't remember what it was left over from, but we still had it in the back of the room. I think they were making some kind of filters or something like that, water filters. And I got something for them to scoop the sand up with. So those are the materials that we needed. The only thing that was a big expense was the cameras. And I actually wrote a grant. I wrote an ACS Hawk grant and got 5 cameras. They're each $300 a piece, and they are not perfect. I'll talk about that. They have a major issue that we didn't know when we started the project, but that's the materials. If you're going to do the physics side of it, then the physics side is going to need some wood to build their machines. We used cardboard to make mock-ups before we built them in wood. You need buckets, and they needed a whole bunch of sand. We used playground sand. That's really cheap because that was the weight. So we poured sand in the bucket until things broke. But that was not a big expense. Oh, and I had different materials like chain and rope and so forth on how they wanted to attach the bar to the bucket. If I back up here, if you look in the picture, you'll see that there's a bucket that they were given. That particular team had a rope that they tied around the middle of the concrete beam. They built prototypes and then decided which their best. That was one of the prototypes. I don't think that was the one we finally used to test things with. Anyway. How do I assess or monitor them during this process? Well, as I mentioned at the beginning, we start with a whole class instruction on concrete. And there's this online formative quiz that sort of reminds them, oh yeah, you should know the difference between mortar and concrete, and you should know a little bit of something about these crystals forming and so forth, and what the heat profile is. Then the whole class gets together to organize the lab, design the mortar bar compositions. This is what I call a challenge lab, in which I basically stand back and the class is doing things. This is not their first rodeo. It's not their first challenge lab. And on that day, there's an exit slip that deals with our school goals of collaboration, critical thinking, creativity, communication, soft skills. You know, I'm sure your school or your department has some set of things there. Even it overlaps with some NGS goals as well. I do share anonymously their reaction to that. You know, they're like, how well did we collaborate? How well did we communicate, and that kind of stuff. We do stuff on that all year long, not just on these kinds of challenges. Then usually on another day, the lab teams, they break up, they figured out their teams, they make the mortar bars, they set up the cameras, they collect the stuff. They come back the next class, which is 2 days later. Mortar bars have dried and they can package them up to ship them. Usually some kids are packaging them up, labeling them and getting them ready for shipping to physics, while the others are looking at the temperature data. You have to do some maneuvering to get the data from the original program it's on that the FLIR collected the data on into eventually into Excel, so you can play with the numbers. And I give them an exit slip on how well they contributed to what was happening with the team. Then the whole class comes together once the data are back, analyzes the results. They have to agree to what their basic claim, evidence, and reasoning is going to be. And there's an exit survey on how that whole process and classwork works. It's a really difficult skill that I can get into later for them to do that. And then they split into their groups and I give them some class time, and sometimes they take some out of class time to develop the oral presentation, et cetera, et cetera. The physics classes actually produce a newsletter for article. And the whole class receives the same grade that is the sum of each of the product teams. So like each team gets a little grade on how well the speakers did, how well the AV did, and there are rubrics for that. You know, how well the display worked, how well the study packet or newsletter or whatever other teams I've got going. And then each individual gets a total of all of those scores. So they are dependent on one another for that part of the score, which creates some interesting discussions. And then after they present, we debrief some more as a whole class. They take their individual test quiz on what's going on, and then they turn in their lab notebook. And then they do a reflection that goes back to, they pick one of the four C's that they really want to work on. Like if they were a leader, they might pick there's a particular rubric that school has for being a responsible member of a group, or being a leader, or being a good communicator, or being a critical thinker. And so they pick one of those and do a slightly more detailed reflection on how well they thought they did. Those are similar to ones that they do for other things. So some of them are continuing. Some kids take the same aspect and keep working on it during the year and keep reflecting on how they're doing. And some kids will pick different things every time. And that's sort of the way I keep track of things. My job is to observe what's happening. I am a consultant when the classes are working as a whole class. They have certain people that are allowed to come talk to me, but they're on their own. Once I give them the original information, they're pretty much on their own to get the work done. But they can consult me on ideas and things that they have. That's just another, that's a more detailed look at, I'm going to back up there. So that's kind of the big picture. My question for you is, do people want to know more about the chemistry, the lab work, the soft skills, the what a challenge lab looks like, what the physics side of it is? What do you want to know more about? Morris, you're muted if you're trying to talk. Oh, okay. Because I can go on in a bunch of different directions, but if there's particular things that people want to know about, I wanted to make sure I covered that particular side of the project process.
I think there's a thread going in the message in the chat where people are contributing.
All right, can somebody,
So, I mean,
Ms. Van der Ven?
we'd love to hear all of it, of course. But, you know, we could sit here and talk about this for hours if we got going. But more specific things, someone's asked what a challenge lab looks like. And someone else has asked what the results were like. Were there obvious conclusions that they found?
Okay.
Did you factor in the time between making it and testing it? Was it kept wet while it was cured? So some of it is like details of the actual making of the concrete, and then just what you did with your students.
I'm going to flip over to results, and then I'm going to come back to the challenge lab stuff, because results is a little shorter. So you can see at the top here, the physics, one of the physics classes, the way they reported things back. That particular class of mine simply labeled their stuff team 1, team 2, team 3, team 4, team 5. They thought that was the simplest way to communicate to the physics class, and they wrapped. It was kind of funny. They took the towels. I've got some like ordinary hand towels in the physics lab, and they spotted those, and they rolled the bars up in them individually and duct taped them. They said that would be safe for shipping. Basically, they had to put them in a milk crate, and then I got them down to the physics lab. And you can see the results for their each replicate. In a couple cases, not available meant that actually the bars never made it. They broke before they could ever be tested. And you'll notice those are the ones that broke with a pretty low weight. So while there was a range of results, there was also some clear differences between composition and strength. And what all 4 classes, chemistry classes, realized is too much sand and not enough water are bad things, right? And all the classes kind of recently realized that if you have too much sand and not enough water, then there's no way that the water can get in between the spaces and start the reactions. You just don't get enough of the CSH crystals forming. That was their hypothesis, that there wasn't enough crystals formation, and so things broke pretty easily. In fact, there was one, my compatriot, he had one group, I think they used something like 75% sand, and they couldn't even get them out of the mold. They were like, overcooked cookies, they just crumbled. So they saw, all 4 classes saw a really strong correlation between strength and composition. What was more problematic was the temperature data. And part of that has to deal with the big problem we had with the FLIR cameras, which was not at all obvious when I researched them or bought them from Vernier. If you look at the top of the camera, you'll see that it has a lightning connection. And that's what, and then if you look below, you'll see that it's the power port, the single port really that's on an iPad or a phone, is what these cameras connect to. So the problem we ran into is that you can't charge the iPad while you're collecting data. So we were only limited to a couple of hours. I wanted to record for 48 hours. I talked to both experts at Vernier and experts at Teledyne, who are the makers of the camera. We tried hubs, we tried splitters. There is no workaround to this. So we are now investigating different kinds of cameras, which are even more expensive, that Teledyne makes for long-term monitoring of temperature. So be aware. I didn't share this with the kids because they had enough to process on their own, that the data we were getting was basically stage 1, the cooling of things when the stuff was formed. The kids did take into account the time between mixing. They had to set their cameras up and place the unfilled mold under it and set the whole camera up, then take the mold away, make it, and quickly get it under. So there's probably 1 to 2 minutes between when they had mixed their mortar and when they started recording temperature. They were pretty good about that. The one team that had problems on that noted it, and the class did a good job of thinking about how that would affect their temperature profile and what that would mean. What they did discover is that the groups that had a bigger temperature drop had stronger mortar bars. It was not as strong a correlation. There were exceptions, but most classes could conclude that. And their thinking was that if they had a bigger temperature drop, then there was more of a reaction happening, right? They got more heat out before it dropped, and therefore more crystals were formed. And I thought at a first stage, for kids that were just barely learning about heat of reaction in the first place, that was absolutely fine. We're going to work for next year on what to do about the cameras. I'm really bummed about that. If I can do something different with cameras, I will. If I can't, then we're going to be really clear that what we're measuring is that first drop, and then we'll try to connect what does stage 1 tell us about stages 3 and 4, because the amount of those first crystals that you form tells you something about the water and the spaces and so forth. There's information I can give them that would help them understand what was going on a little bit. So that was a major, nastiness. You can see an example of one class's 5. There are 5 teams, and this is the same class, and their temperature profiles, and some are cleaner than others. Depending on where they picked the 4 spots on the bars, I think gave them either more or less variation in their data. But I actually was kind of happy about the fact that the data was not great, because I want them to deal with ugly data. Not every experiment gives you stuff where you could say, yeah, pick A. Think about all the data we have on things like COVID. So the fact that they had somewhat cleaner data for the strength and somewhat weaker data for the temperature was not all bad stuff, because it's really more about them learning how to carry out an investigation, work as a team, and come up with supportable claims and figure out what they would do differently or what they would do next. That's always part of our debrief. Not only how would they collaboratively work differently, but what would you do scientifically to investigate this situation further? And they talked about the problems with getting that. They talked about the things that you guys mentioned. They talked about making sure that the mortar got under the cameras right away, about getting cameras that would collect temperature longer, about being more specific about where in the bars the 4 points should be. Would it make a difference if they were at the end of the bars or the middle of the bar, and so forth. And so, they did a good job of analyzing what was going on. On the physics side, we discovered they made prototypes. So in each class made 4 different prototypes. They tested them on sample bars that I had made for them. And then they looked at their 4 prototypes and decided which one was the best. One of the interesting things they came up with is we need to add an extra constraint to their engineering design process, which is make a design that breaks the bars with the minimum amount of force. Because we did find that some of the bars were exceeding the capacity of the bucket. We had to go find some angle iron in the shop to add to the bucket, because the bars wouldn't break with 50 pounds of sand in them, which was pretty much it took like 50 pounds, but I think 40 pounds is about as much as the buckets would hold. But they had to also duplicate, because I was looking at the engineering design process. Once they decided which of their classes designs was the best, one of their product teams had to duplicate that machine so that they had 2 identical machines. So if they were responsible for doing, Mr. Justin's period 1 class, they had to use, one of the physics classes was responsible for doing those. And the idea is that all the data would be on, compatible machines, and so forth. So anything else about results that you want me to talk about before I go to challenge labs? I'm not seeing the chat at the moment, so I don't have access to the.
So we were brainstorming ways around the issue with the cameras, Sue. So.
Yeah, I talked to a Mac expert, I talked to our IT people at school. We did try a splitter, but the data doesn't transfer through a splitter or a hub. And then when I talked to the manufacturer, Teledyne, they said, yep, it's got to be directly connected to, normally it's a phone. Normally these are things that an engineer would take into the field with the phone, connect the camera, and collect static data, not data for a long period of time. Vernier are the people that created the software to collect data over time. And they have now agreed to my request to add that into their description of the device, that it does have a limit. Because when I looked online, it never occurred to me, it says, collect data over time. And it never occurred to me that I would have the limit of the power. You can increase things slightly if you turn down your screen. If you minimize the brightness of the screen, that will buy you a bit of time, and you can get to about 3 hours. The other problem is, of course, if you are not there to stop collection and your device dies, all the data disappears. So instead of I wanted to be able to walk away, come back 2 days later, hit the stop button, and then see what we've gotten. And I'm still looking for a device that will allow us to do that. Meanwhile, the other cameras, everybody else in the department wants to use them for testing plant photosynthesis energy, and the freshmen do model houses and how tight they are. And so the cameras will not, and there's certainly shorter experiments that we can do in chemistry to track temperatures. So the devices are not going to go to waste, but it was kind of the bummer. Anything else on that before I talk about a challenge lab?
Here, I'll unmute for the question. This is Chris Gummo, I teach at Marlboro High School now. How long between making the samples and testing them? Could the students look at variation between like the age of when it was made?
It was really quick.
Okay.
And all of like a particular class would all be tested at the same time.
Okay.
So they didn't have a variation in that. What did happen is because of the availability of the cameras and the place where we were testing, and when the physics class met, some classes waited a week before they got their data, before their bars were tested, and some got their bars tested like 4 days later. But because everybody in the same class all got tested at the same period, that was not a variation. We did not share data between the chemistry classes. It was hard enough to get the data between the chemistry and the physics. And by the way, the reason why I separated the two courses was partly because that's the way it is at Dragon Cement. There's a guy on the 5th floor who gets these little cubes of concrete that he tests, and he never talks to anybody else. He sends them reports. And it occurred to me that there's lots of situations like that. And then, I don't know about you, but my CP kids hate writing reports, right? I have to write my reports. They totally bought into, we got to do a good job of reporting to the chemistry classes, because that's the data have to be good. The data have to be in a clear table. I didn't have to say anything to them on it, because they knew that the chemistry classes, their peers, were depending on them for the data. So it was real for them. The same thing with they wrote articles for our newsletter that goes home to parents, and it's actually a secretary who edits those. So I took the 2 physics classes and said, you're each going to write a report on what you did, and the secretary is going to decide which one's going in the newsletter. She actually thought they were both so good, she published them both, but it gave them, again, like my kids that don't really like to write and don't like to write reports, they totally bought into that part of the project. And of course, my builders loved, they all liked breaking the mortar bars. That was just, that was fun. So yeah, which is more of an answer than you
No,
wanted.
that's what I was curious the time, and if the time had an effect, and also if they were kept. Did you like normally concrete's covered up to keep it moist for a certain amount of time, and was it just put in the
We
mold
did
and
not
left to
do
dry?
that. We did not
Right.
do that. Well, they're so small. These bars are so small that they're completely cured in 2 days. There's really not a whole, you're now in stage 5. So I thought about that and then said, that's just one piece of process too many. It might be something that one of the things about this process is I can keep changing the question. So I certainly can say 3 years from now to my physics kids or my chemistry kids, what if we investigated one formulation, but we changed how long until we tested and the conditions under which we kept it? Is it moist?
Right.
Is it dry? Is it covered? Is it not covered? That could be a whole nother year of the same kinds of, it's the same chemistry, but I don't like to get the exact same question 2 years in a row, because then they're just going to ask their friends from last year what they did. So this project gives me lots of different variations. I can also change, there are several different shapes of molds. Some are shorter and thicker, and some are longer and skinnier. And that's another whole, series of questions. So we did not include that, but it's in the back of my mind as one of those, okay, we need to change up the question. Yeah, because the slower the concrete cures, the better. And I was hoping if I had a temperature profile I was hoping to get it all the way through beginning of
That would
stage
be cool.
5, and
Yeah.
that would tell me, did it take longer or shorter to cure these bars? But we only have 2 hours of data. So I'm really thinking that we've only got, there are a couple of them that come back up. And so like they're just starting, I think, the formation, the stage 3 formation, and the rest of them we're just getting that first stage in the dormancy.
Cool. How about, do you have a statistics teacher that you could collaborate with, or did you? That would be another need.
There really wasn't enough. I mean, you've only got 4 replicates. He's got plenty of data. Our math teachers love science data. So they're always grabbing data from us. This was not a big enough data set for him to be very impressed with. He's been playing with COVID data for 2 years. So he likes to give them big data, but yeah, it's available. Yeah, a lot of he's always wandering over both of them. Well, the stats teacher and also the guy that teaches algebra 2 and does, deals with or algebra 1, wherever when they're dealing with graphs and slopes and things, and he doesn't want canned data. So sometimes he makes them generate their own. He'll do experiments with them, but sometimes he'll borrow our data so that he has something that's not pretty. Let me talk a little bit about the challenge lab process, because that is something dear to my heart. So years ago, I took some classes in what was called education by design. And it was really about collaborative group work, dependent collaborative group work. How do you get groups to work independently, collaboratively? And some of it was actually elementary school. It was a K-12 kind of a thing. And over the years, I've sort of kept and thrown away stuff. So in a challenge lab, actually, let me go here. Before you start any challenge lab, your kids need to know how to discuss science. We actually have a whole thing, it's called productive science talk. How do you discuss things? How do you defend your claim with somebody else? How do you communicate with somebody? How do you challenge their ideas? They need to be able to do that. They need to be able to work safely and productively with a partner in a lab. They need to have some basic understanding of how to write up a CER. So they've done labs and other things with me. We do maybe 4 challenges in a year, and the first one comes at like the beginning of the end of the first quarter, beginning of the second quarter. They also need to expect to be accountable both individually and as a group. If they've never been asked to share a grade, they're going to balk at this whole idea that the product team is the cumulative stuff. So that has to be kind of part of the norms. And hang on, I'm covering that up with my pictures. And they should have experience with it reflecting on soft skills, because I do a lot of that. And by that, I mean things like collaboration and communication and critical thinking, but not content skills. So given that, the basic structure is always the same. They're given a goal. The very first one is they've learned about deviations, accuracy and precision. And we say, we got 4 kinds of thermometers in this room. We got alcohol thermometers, we have EnviroSafe thermometers, we have temperature probes, we have little mini thermometers. Which is the most accurate and which is the most precise? And on that one, you have to give them something really concrete and the way you're going to determine that is to boil water. And the class has to figure out how they're going to boil water. And if they've never done a whole class discussion and you haven't introduced, well, you need some facilitators, you need a scribe, you need to come to consensus on your ideas, you need to figure out how to break up into lab teams, you need to make sure that the experiment itself is super simple. So agreeing on how to boil water works. You'd be surprised. It can take them 60 to 80 minutes to completely organize and understand how they're going to carry that out. the first time. Then they break up and they do the wet work. Then they come back together and they have to decide, what does it mean? What's our claims going to be? And this is really interesting because classes go in different directions. I have classes that like each little sub team to do the work and then double check with one another. I have classes that end up with an expert team that works on that and then explains it to everybody else. I have classes that they try to do it as a whole class discussion where somebody's at front and like, oh, what do we do next? What do we do next? They all develop their own style for how they work as a group. Working as a group of 4 is one thing. Working as a group of 20 is really tough. I mean, if you've ever been on a committee with 20, it's not a simple skill. I think it's a very useful skill, but it's not a simple skill. So they do that. I give them the product teams and the rubrics for that, and I give them class time to work on whatever they're going to do. They come back, and sometimes that's 2 days that they'll work on that. There might be a whole day. There's usually a whole day just for the analysis stuff, and then a day or 2 for the product teams to work. And then they come back, they do their presentation. If at all possible, I get other teachers in, to up the ante. So they have visiting experts. They're expected to do their oral presentation at the level that somebody else who's taking the course would understand. Whereas the hall display is very clearly, this has to be, you have to sell this project to anybody in the building, as opposed to, you got to present this at a conference. It's two different groups with different things. And then, there's all the different reflections and things going on. So that's the way a challenge lab kind of works. Start small, make sure they have the sufficient prior knowledge. Do they know the content ahead of time? Do they know how to analyze the results? I do one a little later on where they make chalk, and they've already done the procedure, which is basically mix things, they form a precipitate and filter them. So they know the procedure, they're just applying it to a brand new question. So, you don't make everything new, or you're going to be there for 4 weeks trying to do this project, and that's not the idea. Lots of feedback, lots of reflection. I'm writing notes while they're doing these class discussions so that I can come back and talk about, how the process worked. I require them at the end, when we debrief, we set up some notes on what did we like about our process and what are we going to change next time. And I bring those notes back when they do their second challenge. You decided that you wanted, like one of the classes this year said, we need somebody to walk between the lab groups on lab day and make sure everybody's doing it the same way, or to answer questions. We want somebody outside of each of those lab groups that walks around. And it's like, you said that, are you going to do it that way? And it's their choice. If they, I give them some suggestions of different roles and things they might do, and lastly, you got to trust the process. The hardest part is sitting back and letting them fumble, and letting them take, I remember one year where it took them 15 minutes to convince the rest of the class that the chalk would be trapped in the filter paper and it would not go through the filter paper, that the chalk was in fact the precipitate. They finally grabbed a piece of chalk from my chalkboard, put water on it, and said, no, chalk does not dissolve in water. They actually had to prove it to people in the class. And I have resorted sometimes to washing glassware at a back sink so that I keep my mouth shut and not interfere with them. This takes time. You can't do all your labs this way. You'll never get any content covered. You have to give up some time to do these. But what they gain in all those other life skills, I think, is really important. And it's also really interesting when you have a student facilitator, you'll find that kids won't respect them. They'll start to have these side conversations that they'll never have if you're up there talking. And then we usually have to have, a debrief kind of intervention on, why were you so rude to Chris when he was up there talking? Would you have done that to me? Oh, yeah, yeah, there's all kinds of things that go on in terms of that they can then apply to being on the student council or, whatever. So I'm very fond of them. I'm nervous this year because my classes have been cut by a third. My honors classes are going from 300 minutes a week to 200 minutes a week. And I will lose at least one of the challenges because I just don't have the time. Things have to go. Got 1/3 less time. I am going to.
So what is the length of your normal lab class?
My length, well, during COVID, it keeps changing. It's like, oh, we're going to try a new schedule. No, we're going to try a new schedule. So it should be about 75 minutes. It used to be close to 2 hours. I had a 2-hour class every other day for chemistry. Physics had 75 minutes and chemistry is now going to have 75 minutes. So this one will still work. Not so sure. Hot process soap may not work. We also making soap as a community project we do, and the hot processing, no way.
Do you have your classes for the entire year, Sue, or just for a semester?
I have them for the entire year. Every other day for the entire year.
Have you done some other molding with the students, like for fun? There's all kinds of silicone molds with Star Wars characters or whatever.
No, we don't have time to do, there's time is my big enemy right now, particularly, in COVID, where I find kids just take longer to learn things.
In particular, if you had the mortar mixed and we're putting it in the other mold, it would just be one other mold next to it to put a little bit, it would be mixing 20% more and putting it in to make something kind of cool and fun that they could take home with them at the end of the week.
Yeah, we might, that's a possibility. I remember that the UMaine students, when they do their engineering day, usually have the kids pour concrete into rubber gloves. So you take home a hand, which is a fun little doodah. But
Sue, one of the questions in the chat too is about what are your other challenges beyond the concrete and the
okay, the first one they do is the accuracy and precision with boiling water. I used to do that where they boiled water and then I showed them how to use condensers and we did the boiling point of alcohol because I wanted to set them up for condensers later on in the year, and it was a nice way. But because of time, we don't do that. The second one is chalk, and it's usually for the honors classes. It's the question is, do you get a better yield in macroscale or microscale? Because they've been working in microscale for filtration things. Chalk is a really simple double replacement of totally safe materials. It's calcium chloride and sodium carbonate, and what you get is chalk and salt water. So it's a great one for that. And they usually get, of course, because we're using the same balances for both sets, otherwise the equipment's just different in size, they get better yields in macroscale, and they've gotten, it's a good summary of where do we lose mass when we're doing things and why do we have to be careful about that. And then we tried for a couple of years, but it's not going to fly with the shorter periods. We did a cool one with extracting the lemonade from lemons and limes. And so that by a water distillation, you basically shred the zest, and you put it in with water and you boil it in a condenser and you collect the distillate is a mixture of the oil and water, which separate in your collection vessel. And you can, and so they ask questions like, each class could come up with each team could come up with a different question. So we had things like, do lemons have more oil in them than limes? Do thick-skinned lemons, are they different than limes? You know, that we had different ones like that. We have done soap making isn't usually a challenge lab because they're not presenting that. We're using it, and then we distribute the soap to either the homeless shelter or the, you know, whoever needs them. Soap is not something you could buy with SNAP stuff. So they all get to take home soap, but then we make, you know, lots more than that, and we distribute it to either the teen shelter or the homeless shelter, whatever needs it at the time. And then, there's one in the spring with, which can either be done with vinegars or Windexes. This year we did it with vinegar, and the question was, can I substitute flavored vinegar for plain white vinegar cup for cup? Do they have the same acidity? And that's a titration lab. But you can do the same thing with, like, is Bargain Windex the same strength as, you know, brand name Windex? That's a great one to do once they should have already done a titration of some type. We do one on salinity, and then when we get to acids and bases, they know how to do titration, so you can determine either the basicity of the Windexes, the ammonia content, or the and they can bring in their own extra vinegars or ammonia-based cleaners, or their final exam, by the way, deals with is a titration of lemonade, which they use for details. So those are the kinds of things that we do. You can email me if there's particular ones you want details of.
Sue, I know I'm just gonna have to ask for that titration lab because I'm thinking about how to change things up with my AP students.
Yeah, and the fun one with that, we do a visual titration. We don't do an electronic one.
Mhm.
And the kids will often bring in as their third, you know, the class gets a little extra oomph if they bring in or sometimes I require them to bring in a third vinegar. So I give them cider vinegar and white vinegar. And if they bring in like a balsamic vinegar, it's dark.
Right.
And then they run into the question. And one year they brought in blueberry vinegar because it's Maine and everything's made with blueberries. And so they have to figure out how to dilute it and come to the realization that, you know, how do I do the calculations to figure it out, what's going on there. You would not have that issue if you did it as a electronic titration, but it is a fun one. And again, you can do, if you do, the first year we did it with lemonade, I brought in the good stuff because then the next day when we weren't in the lab, they had little, you know, I had a jug of lemonade that they could pour out and sip as they were thinking. But don't do that, because if it has pulp in it, it will clog up all your pipettes and your burettes. So we learned that we just use the powders for the labs, but you could do crystal light. I mean, there's so many different titration, you know, anything that's got an acid or a base in it, you could analyze that way.
Cool. Any other questions for Sue?
Oh, yes, Chris, you talked about embedded thermocouples and yeah, so that's why we were using the IR thermometers are just giving us surface temperatures, but
No, it's an interesting how the surface area of the part
problem with
versus
the
size of the part.
thermocouples, because that's how I actually practiced it the first time, is that then you have a hole, which makes it difficult to tense the strength.
You'd almost need a sacrificial sample to put the thermocouple into where everybody has the same geometry and stuff. And then you
Right.
can measure the composition.
And then you have to trust that's going to give you the same data. So that is one,
Yeah.
that is one possible workaround. Yep.
Another easy change up to do in the future to change it year by year would be you could take drywall tape, cut to the width, and lay in a layer or two of drywall tape and see some
Yeah,
differences. It would get touchy for the height and like, you know, where it appeared, but that would be a way to change it.
Yeah, the physics kids wanted me to think about rebar. Here, and we could do it with, wire. We certainly could.
Toothpicks or something, yeah.
But the problem with that is that I don't want to make the mortar stronger
Right.
because we already have problems getting it to break. Although I think if they use a really thin chain or wire as the connector between the bucket and the bar, we will considerably decrease but yeah, I don't want to make it too strong.
Mhm. I tried to do this with clay this year, and my students lost interest. I had to change it up. And
Kristen, do you want to talk at all about some of the other PD coming up?
I certainly could. I can even drop the file. We have a whole calendar for the upcoming summer PD series. And if you give me 1 second, I'll drop that into the chat. Our next session is actually going to be in 2 weeks on the 28th. I didn't schedule anything for next week because I may be on jury duty and I didn't want to schedule anything I couldn't be certain I was at. And so we have one more session in 2 weeks on it's an electrochemistry and thermodynamics activity with Frank Gasparo. And then we have 4 sessions scheduled in August as well. So we've got a lot coming up. There may be more. People keep coming to us with ideas for presentations. So measuring entropy change for a reaction in 2 weeks. And then starting in August, we have a session on using teaching chemistry with storylines and getting started with that. And then on the 11th, Ashley, who I think had a pop out of this meeting, is talking about study habits in her college students and in her general chemistry classes and what she's been doing with those students. And then we have a roundtable discussion coming up on August 15th. We're finding that students are needing more emotional support and behavioral support than ever before. And so having a session on how we can support students in our chemistry classes who are, we're seeing these challenges and they're going through a lot and we're going through a lot to know what we can do. And Sarah English is going to do a storyline on teaching IMF solids and liquids, and that's on August 22nd. So we have several sessions coming up in August and we're really excited about all of them. So we hope to see you at future NEACT events, our summer events, and our upcoming division meetings, etc.
Yeah, and we also have the first of next year's Chem Chats, which are our hour-long open discussions, will be the 25th of August. Yeah, cross your fingers, Kristen. I'm working on snagging somebody for a really interesting division meeting.
Yay.
You read my mind, Sue. I was going to ask you when the next Chem Chat will be in the fall.
Yeah, the next Chem Chat is the 20. I'm keeping them at the moment at Thursdays at 4 to 5 p.m. Although if I find that's conflicts with, somebody's monthly meeting, we can fix that. So Thursday, the 25th, which is my last week of freedom.
Mine too.
And that the topic of that one is, what do you need for the 2022-23 school year? What are your big needs? Because I thought that would help us pick some good topics for the monthly Chem Chat.
To not pull my hair out like I did last year.
All right. I can keep the meeting open for, a while longer if people want to hang out and chat. I'm happy to do that. I think the main presentation is over, but I'm certainly happy to talk chemistry with anybody at any time.
Feel free to email me if you come up with questions in the future. That folder on the Google Drive is not going to go away, so you can access it at any point.
How does one access that Google Drive?
Let me put it back in. Hang on. I think. Nope, hang on 1 second. I thought it was still in my computer's